In section 6.5, we're going to look at rates as accumulation functions. So if you take a definite integral of a varying rate of change of a quantity, that value of the integral is going to give you the net change of that quantity. Let me explain what I mean by this. If you were to integrate, for instance, miles per hour, so that's a rate right there, miles per hour, what you would get as your answer is the total amount of miles traveled on the interval from A to B. And you already knew this because our work in motion told us that if we integrate miles per hour, which is a velocity unit, gets us to displacement, which is miles, a distance. But we're not going to be limited just to motion type problems. We'll be given rates that might be in something like people per hour. But if you integrate people per hour, if you integrate that rate, what you're going to get is the total number of people. So when you're given a rate, such as miles per hour or people per hour, you're actually sitting right here at the first derivative, is your rate. And if you're asked for an amount that is miles or total number of people, then you're going to work backwards. You're going to do an integral, and that's going to get you back to the amount. If you're at a rate and you're asked for another rate, then you're just going to go forward in this list and you're going to do a derivative. So even though we're going to move away from these traditional motion type problems, you're still going to follow that same structure as far as their units go. If you want to find the cumulative effect of a varying rate of change over the time interval, what you're going to do is just integrate the rate, and that will give you the net change in that quantity. So if you're given miles per hour and you're asked how many miles, you just integrate that rate. If you're given people per hour and you're asked how many people, then you're just going to integrate that rate to get back to that unit. So pay attention to the units in this. Sometimes they will help you decide what to do and how to handle the problem. Let's take a look at a few examples. So on example number 1, we have a tank that has 250 gallons of water in it at t equals 0. Water is being pumped into the tank at a rate modeled by this C of t function. C of t is measured in gallons per minute. So I know that that function is a rate for two reasons. Number one, they tell me it's a rate right here. And number two, it has a unit of a rate. At the same time, we have water being removed from the tank. So we have a removal rate of V of t, again measured in gallons per minute. So we've got one rate that's adding water into the tank, and we've got another rate that's removing water from the tank. Part A is asking for the total amount of water that's being pumped into the tank. So I'm just going to focus on this rate that's bringing water in, the C of t. And I know if I want to go from gallons per minute to gallons, because that's going to be our amount, I'm going to have to integrate that rate. Just to call your attention to a few things I've done here, I make sure I write the integral on my paper, so I don't want to just write a numerical answer down. I want to show where it's coming from. And I also didn't write this function, the negative 9, 1.07 raised to the t plus 25 down. I wrote its function name because it's a lot easier and shorter to write. And I also lessen my chances of a transfer error. And also, like we talked about before, it's a good idea to store this into y1 or f1 of x, depending on what calculator you're using, because we're going to be using this function c of t multiple times in the same problem, so it'll just make it a little bit easier for you. And my calculator gives me this answer of 141.012. In part B, again, I'm asked for the amount of water. This time it's removed, so I'm going to use my removal rate, which is V of t. And again, if I integrate this rate that is in gallons per minute, that integration process is going to put me back at gallons, which is an amount. Notice when I'm figuring out how much water is pumped into the tank and how much is removed from the tank, it's irrelevant how much is in the tank at the moment. It's not, the question isn't asking me how much water is in the tank. It wants to know how much is being pumped in and being removed. In part C, now this one is asking me the total amount of water in the tank. So now I have to consider that there's 250 gallons when these pumps begin. So my total amount of water in the tank at t equals 15 is my initial amount, which is 250. Then I'm going to add what's being added. So that's how many gallons are going to be added in, and I actually have that amount up here, minus what's being removed, and I actually have that amount right here, and the net result and my answer is 289.931 gallons. In part D, I'm asked to find the rate at which the water is being removed. So what I'm given in the original problem is that my rate that water is being removed is this V of t function, and it is a rate, and in part D I'm asked for the rate. So all I have to do is plug in t equals 6 into that rate function. Most of the time you're going to have your calculator for these rate problems. Make sure that you say what it is you're doing on your calculator. So writing V of 6 is a necessary part. Don't just write an answer. Say I'm going to take 6, plug it into my V, and then let the calculator do the work. And this is a rate, so gallons per minute is my unit. In part E, I'm asked if the amount of water in the tank is increasing or decreasing at t equals 6. And what I know is that a function is increasing if its derivative is positive and decreasing if its derivative is negative. So if I want to know if that amount is increasing or decreasing, I need to look at its derivative and see if I get positive or negative. So these rates that I'm given in the original problem, that C of t and V of t, because they're rates, they are the first derivative. They are the derivative of the amount. So I'm just going to look at C of 6 and V of 6. And you can use a little common sense and make sense of this answer. If my water is coming into the tank at this rate, 11.493 at this particular time of 6, and it's being removed at a rate of 6.788, because it's coming in faster than it's being removed, that water level is going to rise. My amount of water is increasing because C of 6 is greater than V of 6, and that's just saying that water's entering faster than it's being removed. In my last part here, I'm being asked if the rate at which the water is being removed from the tank is increasing or decreasing at t equals 6. Notice it's not asking me about the amount like in part E. It wants to know if the rate, wants to know if V of t is increasing or decreasing. So just like what we said over here on the side, I will know if V is increasing or decreasing by looking at its derivative and seeing if it's positive or negative at my time in question. So I need to find V prime of 6. As we said before, if you have a calculator and you're finding a derivative at a point, it's understood you're going to use your calculator to do that calculation, but you have to write on your paper what you're telling the calculator to do. So this V prime of 6, I get a negative value here, which means to me that V is decreasing because its derivative is negative. And then I just sum up my answer. My removal rate, that V of t, is decreasing because its derivative, V prime at 6, is less than 0. For example number 2, I just threw this one in here so you could see that we can actually do this in any sort of a storyline. So in this one, again, I'm given a rate at which people enter an auditorium is modeled by this function R from 0 to 2. R is measured in people per hour. So that just confirms I have a rate because it's got that rate unit. Tells me that 100 people are already in the auditorium. That's my initial amount at t equals 0. The doors close, concert begins at time t equals 2. The question wants to know how many people. So I have a rate R of t that is people per hour, and I'm asked how many people. So just analyzing the units tells me that I'm going to need to do an integral. The integral is going to accumulate all the people that are entering from 0 to 2, but then I have to also consider the 100 people that were there beforehand, so I need to add the 100 to this. And then putting this in the calculator to get an answer gives me 1,080 people. Let's take a look at example 3. Initially, when you look at example 3, it looks a lot like example 1. I have a tank with water, 300 gallons to begin with. Water's being pumped in at a rate modeled by this function called K. Gallons per minute, there's my rate unit. However, my second function that's given is actually an amount in gallons. So this function C is not a rate, it is an amount. So the rate is already sitting at the first derivative, so K is already at that first derivative, but C is that original function. So just check to make sure if your functions are rates or amounts, and here I've got one of each. Part A is asking for the amount that is pumped into the tank from t equals 0 to t equals 11. Because my water being pumped in is a rate, the K is a rate, gallons per minute, I know that I'm going to do an integral to get that back to gallons. But now when I get to part B, and I'm asked for the amount the water's being removed, my removal information is actually an amount of water. So C of t represents the amount being removed. So I don't have to do anything to that function except for plug that 11 into it. So again, the difference in part A and B was when I'm asked for the amount of water being pumped in, because that water being pumped in was given to me as a rate, I needed to integrate the rate to get back to gallons. But in part B, because my amount being removed was given to me as an amount, I simply had to plug the 11 into that function. In part C, I'm asked for the total amount of water at this time t equals 11. So if I want the total amount of water in the tank, I need to consider everything that's going on, which is that there's 300 gallons in the tank to begin with, and I have some water being pumped in, and I have some water being removed, and I need to account for all of this. Here's what I get when I put all of that together. 300 is my initial amount in the tank. This integral of that K of t, which is a rate, will give me the amount of water that's added, and I'm going to subtract because this is what's being removed. C is a function that is an amount, so I don't need to do anything with C except for plug that 11 in, and I get my final answer of 356.973. Make sure that you don't just pull these answers down. I would say go through and recalculate the integrals. If you use rounded answers for your intermediate calculation, sometimes that starts to affect the accuracy of your final answer, and we need this guy to be accurate to 3 decimal places. In part D, I'm asked if the amount of water in the tank is increasing or decreasing. So I'm going to compare the rate of water coming in with the rate of water being removed and see which one is higher. Just plugging 11 into my function k, because k is the rate, gives me 6.056, and that's the rate the water's coming in. Because function c is the removal amount, to find the rate of removal, I need to do a derivative and then plug the 11 in. My rate of removal at t equals 11 is 1.227. So if my rate in is faster than my rate out, it makes sense that my amount, my water level, is going to be increasing because water's entering faster than it's being removed. The difference in this one is just knowing when to do a derivative and when not to do a derivative. On our last question here, we're asked about a maximum amount of water. So I have a tank that has 40 liters at t equals 0. Again, I've got water coming in at a rate that's modeled by F, liters per hour. I've got water being removed at a rate, so both of these are rates in liters per hour. But this time I want to know what is the maximum amount of water in the tank along this time interval from 0 to 5. This problem is an absolute maximum in disguise. What we need are critical points and endpoints, and then we're going to find the amount of water at each one of those times and then just pick the largest one. So you're going to find critical points just like you always have. We're going to take the derivative and set it equal to 0. So the derivative of the amount, because that's what I'm looking for the maximum of, is the rate that's given, and I'm going to set that equal to 0. And I have to consider that one of these rates is adding water and one of them is taking it away. What we're looking at right here is our derivative set equal to 0. To solve this, I'm going to add the g of t to the other side. And I'm solving this equation where f of t, that's this exponential function, equals g of t, which is this exponential function. It is a hard equation to solve, but when you have your calculator, it's super easy. So what we're going to do is put f of t into y1, g of t into y2, and then find their intersection point. The calculator gives me that intersection point is 1.465. That is a rounded answer, and I don't want to use it any further calculation, so I'm going to store it into a dummy variable that I'm going to call a. Now I get my candidates table going. I have a column for my t values, and I have a column for the amount, so I'm going to put in my endpoints, which are 0, 5, my critical point, which is this 1.465. Because I've defined it as a here, I can call it from a here on out. Here's my short list of candidates for the maximum amount of water. I know it's going to happen at one of these times. What decides which one of these is the maximum is how much water is in the tank at each of these times. I know at t equals 0, the amount of water is 40 liters. For t equals 5 and t equals a, I have to do a little bit more work. Just like I had done previously, the amount of water is going to be represented by what's in there initially, plus what's being added, the amount added, minus the amount subtracted. Because f and g are rates, I need to do the integral of them to get back to the amount. So this is the calculation for t equals 5, and this is the calculation for t equals a. I've got that a stored in my calculator, so when I type this integral into my calculator, I just have to call up a. And the amounts that I get are at 5, I get 18.350, and at t equals a, I get 48.487. And I can see out of these three amounts, the largest one, the greatest amount, is happening right here. And then I just sum that up as my answer. My maximum amount of water is 48.487 liters, and it occurs at that time of 1.465. For these types of problems, you really have to be aware of rates versus amounts, which one you're at, which one you're looking for. And also, if you're using your calculator to evaluate these answers, you'll want to make sure that you put a little bit of work, show what it is that you're solving on the calculator, whether it's an equation or an integral or derivative that has to show up on your paper along with the answer.